All right, it's 4 o'clock. We will give everyone a couple of minutes before we begin. All right, I guess we can start. Welcome, everyone. Thank you for taking the time to attend this VLE. So today we're going to try to take part in a Kaggle competition. So full disclosure, this Kaggle competition, unlike many others, is not live and there's no cash prize associated with it. So if you do really well, all you get is earn is bragging rights. But hopefully this will serve as a useful exercise for when you decide to actually take part in real competitions. So hopefully you have, another thing is if you want to sort of use this as a code along, that's great. And if you don't, I appreciate how it can get a little bit tricky. You might have to have two screens and might be a little bit difficult focusing on what I'm doing and what you're doing at the same time. So you can just watch and follow along. And if you want to follow along later on, all of this will be recorded. So to begin, you have to have a Kaggle subscription, sorry, a Kaggle account, but you don't need to pay for it. It's free. So this is what the homepage looks like. So Kaggle primarily hosts these competitions. I believe that's how it started off as this place that would host competitions that people would take part in. So if you click on competitions, you can see that there are many active competitions with some pretty decent prize sums. And these run the gamut from like pretty simple linear regression problems to sophisticated cutting edge computer vision tasks or NLP or any of those things. Another great thing that Kaggle offers is it's a repository, a giant repository of data sets and all kinds of data sets. So these are some of the trending ones, but they have like COVID related data sets and gene expression data sets and things like that. And this is a relatively new feature of Kaggle, is they have a courses page. And as you can see, I've taken part in, I've almost completed a few of them. And these are really useful. They're excellent. I recently completed this machine learning explainability course, and that is especially good. All right. So, oh, and finally, maybe the most useful thing, at least for me, about Kaggle is everyone else's code. So you can see people tend to, I think it's just restricted to Python and R, but you see, especially people who do really well in these competitions, many of them make their notebooks publicly available. So you can see how some of these top performers do what they do. And in addition to that, many people just make data sets for the purpose of explaining some concept. So those notebooks are even more useful. Okay, so that is an intro to Kaggle. So to take part in this competition, you go to the competitions page, and then we can just search for it. And the name of the competition we'll be taking part in is called Kannada MNIST. So click on it. And so just a little bit of background about this data set. So Kannada is a language. So I was born and brought up in the city of Bangalore, and it is the local language of Bangalore. Unfortunately, for whatever reason, I cannot speak a word of Kannada. So this is both personally meaningful to me and might actually be useful. So the MNIST refers to the fact that this data set contains handwritten numbers in Kannada. So numbers from 1 to 10, and you can tell, like, this is how you would write 1, 2, 3, and this is 1, 2, 3 in Kannada. So as you can see here, they're asking you, are you bored of MNIST? It's because MNIST is kind of like the hello world data set of deep learning. And it's a really useful data set to use to teach various concepts, but it's also, because it's used by everyone, it's kind of boring. So I will go through some of the details of this data set as we go along. So to begin taking part in this competition, all you have to do is click on code, and you can see this new notebook button, and just click on that. Also, feel free to please ask any questions or interrupt me or anything like that. I'll either answer the question as it comes, or I might batch them because there'll be a little bit of downtime, especially when we're training our models. So hopefully you can see this. If you are familiar with Jupyter Notebooks, this is effectively a Jupyter notebook. Also, if you are familiar with Google Colab, this should all be really familiar. So we begin with this. They give you this sort of random name. And if you want to save give your draft a name, I can call it MSBLE or something like that, and give it a date. And you can just save as you go along. You can see that it's already populated our notebook with some code. And this code is really useful. What this code produces are these paths that tell you where to find your training data and other useful data. So before we begin, let's just set a couple of things. Now, in the instructions for this competition, they ask that we switch the internet off. And what that means is, so that's just here setting it to the minus sign. What that means is when we switch it off, we can't, for example, download something from another website through our notebook. So this, for whatever reason, is not allowed. So we just make sure to switch that off. It won't affect, entering and executing code and all of that stuff. But when it comes time to submitting, you will encounter an error. So do that. And the second thing is, because this is deep learning, let's use a GPU. And they'll give you a warning. They'll say that we're restricted to 37 hours a week, which is pretty generous. I've already used 46 minutes this week. And that's one of the great things about Kaggle. All you have to have is a computer and access to the internet. And you can use things like GPUs, and you can do everything within their environment. So you don't even have to have things like Python installed or anything like that. All right, so let's begin. I think the session started. So what you can do is, so this is a code cell. And to run it, you can just click this play button. You can see that it worked pretty quickly. It gave us the output is these 4 paths, which we will use for importing steps. Now, a notebook consists of Markdown cells and code cells. So Markdown is just this format here that allows you to put in human readable text. So you can do all kinds of things with Markdown. You can put in hyperlinks. You can format your notebook so that it looks nice. You can put in lots of explanatory text. That's really useful both for other people and for your future self. For this notebook, I'm just going to put in headers. So I'll do something like data import and pre-processing, right? And so it looks like that. It's the hash, the pound symbol at the start made it a header. So now we can use, and so to make a Markdown cell, all you have to do is click Markdown, and to make a code cell, you click the code, plus code. So I've made a code cell here. And what I'm going to do now is I'm going to import the training data set. So that is conveniently named train.csv. So to do that, I'll create an object called train, and I'll use the package pandas. So one of the things I hope to do in this VLE is give you a whirlwind tour of many of these really useful packages for machine and deep learning. So Pandas certainly is one of them. And in the previous code cell, they had already imported Pandas for us. They'd imported three packages, two of which are Pandas and NumPy. And it's conventional, it's convention to import these packages to alias them using this PD and NP respectively. So we use the read CSV method from the pandas package. So we do pd.readcsv, and then we have to give it a path. So since this is the train set, I'm just going to copy paste this rather long path and remember to put it between inverted commas. And that's it. That's the, that'll do the importing. And then if I want to see what the first few entries of this train object is, I can just do train.head. If I run all of this, it's going to take a second because I don't know how big the CSV file is, but it's a little big. All right, so it's imported it, and now you can see the first few rows. Each row corresponds to one image. And the first column gives you the label of that image. So in this case, the first row, the label has a value of 0. So that means the number 0 written in Kannada. And the remaining columns have the pixel intensities. And this is I skipped over this. This is a 28 by 28, I believe, yes, image. And what they've done here is, because an image is two-dimensional, to be able to put all of these data into a tabular CSV format, what they've done is they've taken this two-dimensional image and they've stretched it out so that it's just one long string of pixel values. And that'll actually be useful. So what we'll do is we'll train a baseline model just to get a sense of what some of our code is doing, and then we'll build a more sophisticated model. All right, so that's the train. We can just leave that as that. We will also need a test set. And so actually, so they have a train and a test set. I'm trying to think. Let's ignore the test set for now. And we can use this dig MNIST set as our test set. And the reason I hesitated is because the train set and test set, as they're given there, the original data were taken from the same pool. This dig MNIST is, I forget the details exactly, but these images were generated by other people using, I think it's like a different scanner, and they were intentionally made to be images of poorer quality, I believe. So this is kind of like a really harsh test set. So if you do well on this, then your model is probably really good. So we can just use that as our test set. And so to do that, we can just do the same test equals pd.read CSV. And we put in this path and we leave everything else the same. Actually, if we want to take a look at the test set, just for the sake of being thorough, we can again do the test.head, and we see that it has the same structure, the label and then pixel values. Okay, so that is our data set. So right now, we've imported our data, so our train and test sets. So these are pandas data frames. We will need to convert them into NumPy arrays. And so NumPy stands for numerical Python. And it is a package that allows us to deal and manipulate n-dimensional arrays. So an array is just a catch-all term for scalars, vectors, matrices, and then multi-dimensional arrays. And this is just it's a very convenient way of handling our data for like machine and deep learning tasks. So to convert the pandas data frame into a NumPy array, that's really easy to do. So we'll do that. And what we'll also do is we'll split this data frame, the trained data frame, into our labels array and a input array. So we can call the input, and the input array is just the pixels that make up the image. So we can call it xtrain, and we have our train data frame, and we can use the iloc method. And so what this does is, so if we do : 0, what this does is it takes all the rows, but only the first column. So it's just taking our label column. And so that's, and then to convert it to an array, we just use the two NumPy. And we do the same thing for, we can do y_train. We do train.iloc. And again, we want all the rows. But this time, we want all the columns except the label column. So to do that, we just do 1 and then colon. And that's it. And then we want to turn this into a NumPy array also. So we do that. And then we can do this for the test set also. So I am just going to copy paste, making sure that I remember to change everything. So you just change all the trains to tests. And then if you just want to, actually, let's go ahead and do this, make sure that there are no errors. While that's running, I'll just open the next code cell. So that looked fine. I didn't see anything that looked off. So what we can do now is we can take a look at the arrays that we've just made. So for example, xtrain, if you just wanted to literally just see it, you could, oh, I'm sorry, this is a mistake. It's the other way around. So it's what I called xtrain is actually ytrain because those are the labels. And so my mistake. So please change the y's to x's and rerun this. So this is why it's obviously always good to immediately take a look at what new objects you've created to avoid. This would have been disastrous later on if I hadn't spotted this mistake. It's taking a little while to run. And now when I run xtrain, I should hopefully see something different. I do. I see this, it's now an array object and it's two-dimensional. This is a little, because it's such a big object, this has limited information. So there's this one really useful method called shape. And what shape does is it tells you how many dimensions your array has. So in this case, there are 2 numbers here. So that means 2 dimensions. And the first number tells you how many rows this array has. So 60,000 rows. So that means there are 60,000 images. And the second number, 784, tells you that there are 784 pixels in each image. And similarly, if you wanted to take a look at your Y array, your labels array, you would just do the same. And in this case, you don't have something that's an array that's 2-dimensional. You have a 1-dimensional array or a vector, and it too contains 60,000 elements. So those are the 60,000 labels, and the labels are just 0, 1 up to 9. Okay. We can now just quickly take a look at an example image. And for that, we need to use another package. So we can use this, we can use pyplot for that. So we do import matplotlib.pyplot as PLT. And we'll be taking a look at just one image for now. So let's say we call it 1_image is equal to. What you can do is, so for xtrain, let's say you wanted the 50th image, you just do x underscore train, and then in square brackets, just enter 50. And so one image will be the 50th image. And to actually see that image, you can use the imshow method, the plt.imshow method. And then you just pass this one image. And we will pass another argument. So the parameter is cmap, so color map, equals gray. And this is because if you don't do this, actually, let's do it without this and see what we get. And if we run all of that, we get an error message. And the reason we get an error message is we're trying to plot an image. And an image is, in this case, it's two-dimensional. But the data came in this one-dimensional format, this stretched out pixels. So what we have to do is we have to convert that one-dimensional array into a two-dimensional array. And so to do that, this one underscore image, we can use the reshape method. And we know that each image contains 784 pixels. And just because that's such a like traditional MNIST number of pixels, the square root of 784 is 28. So we do 28 comma 28. So now we turn our one-dimensional array into this square image. And now if we take a look, we see that it's the well, I don't even know if that's a number 0 because this is Kannada. We're going to find out what this is. And actually, if you wanted to see what the label was, you could do white train and also just look at the 50th, the 50th entry. And we see that, oh, it is 0. Nice. So I mentioned that this, I mentioned that these are black and white images, but this is clearly not black and white. And that's because by default, plt.imshow gives you kind of this heat map. And so those pixels have a high value and those pixels have a low value, the background pixels. So we can just kind of force it to be black and white by setting the color map to be gray. So that's kind of what the original image looks like. Okay. Before we actually build our first model, we need to do two more things. One is, so all of these values I mentioned are between 0 and 255. And if we just used the data as is, it would still be fine. We'd be able to train our models and nothing disastrous would happen. But in machine learning, it's generally a good idea to have your features all be on the same scale. So we can, or similar scales. So we can, so you can see like a lot of the pixels, for example, let's say in the top left-hand quadrant, they're all probably going to be around 0 because the examples tend to be numbers written in the middle. So they will vary from, let's say, 0 to 1 or 2. Whereas pixels in the middle, depending on what number you're writing, are likelier to range from across a much bigger range. So like 0 to 255. So one typical standard pre-processing step is to make everything be between 0 and 1. And to do that, it's really simple. So we can just override our xtrain object. We can do x_train equals x_train and just divide it by 255. And so now all the values in x_train will be between 0 and 1. We have to do one more thing, and this is particular to, so I didn't mention, but we'll be using TensorFlow and Keras to build our deep learning models. And TensorFlow and Keras are expecting, so the neural networks we will make, they are expecting objects of type float 32. Anyway, I won't go into the details of like what 32 means or 64 means, but that's just the object type and the precision that they are expecting. So to give them what they are expecting, we just do x_train equals x_train dot as type. And we just specify that it's float 32. And we can go ahead and do this for our test set also, just so that we don't forget later on. You can do x_test. So again, just quickly copy paste and make sure you change all the trains to tests. And we run this, and that's great. So now we're ready to build our first model. So what I'm going to do, I'm just going to call this baseline model. And I mentioned that we're going to use TensorFlow. So we now need to import a few things from TensorFlow. Well, let's first import TensorFlow itself. So we import TensorFlow as TF. So just quickly, why is it called TensorFlow? So I mentioned this concept of n-dimensional arrays. Tensors are kind of another word for n-dimensional arrays. So NumPy offers us this very convenient way of representing data in all of these different forms and manipulating them really easily. But we can't use the GPU using just vanilla ND arrays. So to do that, we have to use tensors. And the flow part comes from the fact that neural networks and a lot of these models are just data transformation. As you put in your input data into your model and it gets modified, and then you make some kind of prediction. So the flow refers to the fact that your tensors are flowing through your model. So I think it's a nice name. And then you import TensorFlow as TF, and then from TensorFlow.keras, .models, so there are different kinds of models, we will be importing sequential. Now, TensorFlow and Keras offer, so what is this? So I kind of described TensorFlow. What is Keras? Keras is built on top of TensorFlow, and it just offers a much more user-friendly, or at least beginner-friendly interface for building these neural networks. That doesn't mean that it limits the kind of neural networks you can make. You can still do very sophisticated things, but it just, as you'll see, the code is relatively readable and compact. So there are different ways of building models in TensorFlow. The easiest way is sequential, because if you're familiar with neural networks, it's just one layer after another. So it's these layers exist in sequences. So sequential is just a nice way of thinking about it. There are two other ways of building models. There's what's known as the functional API and the subclassing API. I will cover neither of those today, but if you want to do more sophisticated things, like let's say you have had two different types of input, let's say both images and text. So you need your neural network to have two arms, and then they have to come together and merge at some point. Then you're better off using one of those other two APIs. But for today, sequential is great. And the last thing, or rather the next thing we will import is from TensorFlow.keras.layers. We need to import these layers that I've been mentioning that make up the neural network. For now, we can just do dense. And a dense, so if you're familiar with a multi-layer perceptron where you just have a bunch of input neurons, and then like hidden layer neurons and output neurons, where each neuron is connected in one layer is connected to all the neurons in the next layer via a weight or weights. That's what this is. This is the dense layer. So we do this, and then we can start building our model. So we can call our model, let me call it, baseline is fine, is equal to sequential. And this sequential model takes in input in the form of lists. So so what you do is you do sequential and then open close parentheses, and then you have to remember to put in square brackets because you're entering a list. And within that list, so in this case, I'm just going to make a super simple model that has 784 input neurons because you have 784 features, and 10 output neurons because you're making 10 predictions, 0 to 9. So we do dense. And the way it works is you put in dense, and then the first number refers to the number of output neurons. So we want 10, so we put in 10. And then we can put in this optional argument called input shape. I think it's nice to put it just for the sake of completeness. And it has some nice, there are some benefits to specifying the input shape that I might skip today, but it's just a good idea to do. It's also nice because it it ensures to yourself that you know what's going on. So we do input shape, and the input shape refers to the dimensionality of each entry. So in this case, we're just putting in a string of 784 pixels. So it's a one-dimensional array. So it's just a vector. So that'd be 784, and we have to put comma. So that's how we represent a one-dimensional array. And then, so if you have attended any of the previous, or not any, but if you've attended a previous talks on an introduction to deep learning, hopefully you will have come across this concept of, so in this case, we're doing multi-class classification. So what we want is we want to output what probabilities of each class. And then the aim of the game is simple. In this case, we have 10 outputs. So we want to output 10 probabilities. And we pick the one with the highest value, the highest probability. That's our model's prediction. That's a nice, simple way of picking a winner. So to do that, to make sure that our output is in, they're all probabilities, meaning that they all, if you add up these 10 values, they all add up to 1. We can use what's known as a softmax function. So we do activation equals softmax. And that's all softmax is doing. It's just compressing values to be, to all add up to 1. And so that's it. That's our baseline model. So that's how you build it. Seems like overkill for such a simple model, because it kind of is, but you'll see how using this framework or the structure, we can make something more sophisticated. So we have a baseline model, and then what we want to do is we want to compile it. So we do baseline.compile. We need to specify certain things here. So we need to specify our loss function. And this is a way of defining how good or bad our predictions are. So if you think of a neural network as like an orchestra, your loss function is the conductor. And so in this case, again, sorry for glossing over the details, but really the mathematics, like the actual functions themselves, are super straightforward to understand, and the TensorFlow and Kara's documentation is excellent. So we'll be using this thing called categorical cross entropy. And in this case, we'll use a specific type of categorical cross entropy called sparse categorical cross entropy. And the reason it's sparse is our label values are all individual numbers. To use categorical cross entropy, they would have to be what's known as one-hot encoded. Again, I'm just going to mention that and then go ahead. So we do sparse. So it's a bit of a mouthful, categorical underscore cross entropy. And then we need a way of, for our model to learn. So again, if you're familiar with any of this, you will have heard of gradient descent, stochastic gradient descent. We'll be using a similar approach, but we'll be using a better optimizer. It's called Adam. And again, Adam is typically preferred to just vanilla stochastic gradient descent for various reasons. So it's a good default optimizer to use. And then we have, so those are the two, like that's the bare minimum we need to put in here. But we can also put in something useful for ourselves. We can put in one or more metrics. So this is slightly different. We do metrics equals, and then we create a list, because we can supply or ask Keras to work out multiple metrics. In this case, we're just doing one, but we still have to provide it as a list. So we do metrics equals, and since we're doing a prediction task, we can just do metrics equals accuracy. If this were a regression task, we could use mean squared error or mean absolute error or some other such metric. So that's baseline.compile. And now we're almost ready, or we are ready to train the model. So to do that, we do baseline.fit. And we have to give it our training set, so x underscore train, our labels, so y underscore train. And then we need to specify how many rounds we want to train this model for. So that's epoch. So that one epoch refers to passing all the data through, training data through our model. Again, if you're familiar with this stuff, you will know that there's another argument called batch size. If you don't specify batch size, which I'm actually going to skip now, the default batch size is 32, which is a reasonable number. But that's another so-called hyperparameter that you would have to test yourself. So we can just do epochs equals 10. This is another thing. Epochs, number of epochs is another thing that will require fine tuning. And finally, so we have a training set and we have a test set, but we need, like, our test set has to remain kind of pure. Like, we only look at it once at the very end before we're ready to submit. So, but we need a sense of how well our model is doing. And just relying on the train set's a bad idea. Training set is a bad idea because we can run into this problem known as overfitting. So that means we can get a model that performs amazingly well on a training set, but is useless on some other data set. So we say that it doesn't generalize well. So to do that, we can kind of create for that, we create what's known as a validation data set. Now, we could have done that previously, but Keras offers this nice feature here. So this validation data equals oh, I'm sorry, not validation data. My mistake. That's if we actually had validation data. What we could do is we can just do validation underscore split equals, and then you can give it a fraction. So this refers to how much of the data you want to use for validation and how much you want to use for training. So this is a balance, a fine balance. If you use too little data for validation, it's kind of hard to trust your validation metrics. If you use too much, then you don't have enough data to properly train your model. So 0.1 seems to be a reasonable value. Now, we could run all of this and everything would be great, but wouldn't it be nice to have some kind of memory of what we're doing? So to do that, we can do history. We can create what's known as a history object. So we can do just history equals, equals baseline.fit. So, and then I'm just going to run this and hope there are no errors. So it's running and, oh, of course there's an error. Sorry. Oh, spelling mistake. So I misspelled categorical. I hope that's the only mistake. Yeah, so you can see it gives you these nice kind of status messages where it shows you after each epoch what the accuracy on your train set is, what the loss is, what your validation loss is, and what your validation accuracy is. And you can see that it, like, even just this simple linear model is doing pretty well. So that's just 10 epochs. All right. So I mentioned that we created this history object, and this history object it's an object that's known as a callback. And there are many such callbacks in Keras. I might get to one particularly useful one in a second, but what we can use this history object for is we can use it to plot our loss and accuracy curves. And this is really useful because I mentioned the ever-present danger of overfitting. So plotting your loss curves is one easy way to detect whether you have overfitting or not. So just to quickly go through this, we can do, we can create a train accuracy object. And we just do history.history. And then to get our train accuracy, we just put in accuracy. And to get our validation accuracy, we can do val underscore accuracy is equal to, again, sorry, this is a little repetitive. Every time you want to get something out of your history object, you have to do history.history, val accuracy. And then similarly, again, copy pasting is never a good idea. We can extract our loss values after each epoch and just convert all the accuracies to loss, so train loss, validation loss, and then val loss. And then to be able to make this plot, we need to plot our accuracies and losses against epoch number. So to get the number of epochs, we can just do epochs equals range length of the train accuracy. And now we can just plot this. So let's plot the accuracy first. So we use pyplot again. Let's do plot plt.show. And we want epochs to be on the x-axis and train accuracy on the y-axis. And then we can make this blue so that we know blue is train. And we can do the same for the, further validation accuracy, and we can make this green. And we can give it a title, accuracy. And actually, let's just go ahead and make the loss plots, loss curves also. So do call it like loss plot. So here you just can change all the accuracies to losses. We run all of this, get an error. Oh, it's not. I'm sorry. I'm speeding through it. It's plt.plot. And oh, sorry, it's doing it on the same figure. So you do plt.figure. All right, so you can see with the accuracies, you started off, so green is our training set accuracy. You started off really well and you continue to do really well. For validation, it went up and it's continuing to go up. So this is a good sign because typically with overfitting, especially if you look at the loss plot, so again, you see this nice decrease in loss for both the validation set and the training set. So typically with a sign of overfitting, is you'll find that the loss curve for your training set will keep going down, but your validation set at some point, the loss will start to go up. So that point of divergence is when overfitting starts. That's a bad idea. So in this case, we only train for 10 epochs and it's a pretty simple model. So we were unlikely to run into overfitting issues, but these plots are essential. Always plot them. Okay, we have 18 minutes. So let's make a convolutional neural network because those are they perform very well. Just call it CNN when it comes to these image tasks. And even though we only have 18 minutes to go, I'm going to hang around afterwards if there's any questions, but I don't want to run over. All right, so for CNNs, again, like it's a 30-second introduction to CNN. If you aren't familiar with these things, they're just a specific type of neural network architecture that was designed for image analysis. And again, just like so what we did here was multi-class logistic regression. Just as for that, we have weights and biases. The difference is the way we organize those weights is different. And we organize them as these two-dimensional filters, also known as kernels. And these filters learn to detect some basic features, image features. And they scan your image to search for those features. And then we put in multiple layers because like nature is compositional. Images are compositional, meaning that even the most complex, sophisticated images are all made up of simpler building blocks, like vertical lines, horizontal lines, and so on. And so the convolutional neural networks begins by learning to detect these simple features and then puts them all together and starts to learn more complex features and more complex features and so on as you go through the network. Tim Dunn gave a talk on CNNs a couple of days ago. So if you want a good introduction, you can watch that. So that's my slightly more than 30-second introduction to CNNs. So we have pretty much everything we need already to build a CNN, except for the CNN layer itself, or the convolutional layer itself. So to do that, we from, again, Tensorflow, errors.layers, we'll import two things. We'll import a two-dimensional convolutional layer, 2D because it's a two-dimensional image. Believe it or not, you can apply, you can use convolutional neural networks for text analysis. And in that case, you would use a conv 1D, but we're using conv 2D here. And we'll use this other layer called a max pooling layer. And what that does is it just takes the output of a convolutional layer and just reduces its dimensions. And this is a nice way of making sure that our model doesn't get too big. And it's also, you can think of max pooling as a way of keeping the signal and getting rid of the noise. All right, so then now it's just repetitive. We define the structure of our model. So we'll call it CNN, and CNN equals sequential. And remember, this is how we're building our model. And we enter in a list. So it's sequential, open close parentheses, and then open close square brackets. And this time the input is conv2d. And it is taking in, so in this case, the output, we have to give it a couple of new arguments. One is, I mentioned this concept of filters. We have to define how many such filters we want our model to learn. That again is another example of a hyperparameter that you would need to fine tune by testing out various combinations or various values. So I'm going to do 32. I know that from past MNIST experience and what I've seen other people do. So we need to specify, and actually, let's be thorough. I think it's, I can never remember this. I think it's filters equals 32. And then we need to specify the dimensions of the filters. So unfortunately, the parameter is not filter size, it's kernel size, because these things are sometimes called kernels. Anyway, and this is two-dimensional. Again, kernel size is another thing that you will need to fine tune, but 3x3, 5x5 seem to be pretty good values. We'll do 3x3 just to keep the number of weights small. And then we need to specify an input shape, just as we did previously. So I realize here that I have jumped the gun. So I'm just going to leave this here as is and insert a code cell right before this. And the reason for that is this model is expecting a two-dimensional object. And as you recall, our xtrain and even our xtest are one-dimensional. So we need to reshape them. So just to remind you what xtrain, the dimensions of xtrain are. So it's x_train dot shape. So 60,000, 784. What we need to do is convert it to be two-dimensional. So we do that by doing, again, x_train is equal to x_train dot reshape. This is where NumPy is so powerful. Now, there are a few ways of reshaping it. So our target dimensions need to be the following. First number refers to how many samples we have. So that's 60,000. Second refers to the height of our image. So that is 28 pixels. And the third is the width of our image. That's also 28 pixels. And unfortunately, I don't know why, unfortunately, but you would think that this is all we need. So now we have from one-dimensional to two-dimensional. We also have to specify what's known as a channel dimension. And because this is a black and white image, it has just one channel. So we put in 1. Doesn't feel like it adds anything, but our conv2d layer is expecting this 4-dimensional object. So number of samples, 28, the height, the width, and then the number of channels. And that's it. We just have to do that. And then while we're here, sorry, X test. Let's change X test. Let's reshape X test also. Here's one thing. Now, I've forgotten how many entries there are in X test. In the event that you do, what you can do in NumPy is you can ask NumPy to infer the value. And this is a little tricky at first, but basically what you do is for the dimension whose value you don't know or forgotten in my case, you just put in a -1. And then you put in everything else as you would otherwise. And what this does is it kind of works out based on what the values of the other dimensions are, what this dimension should be. It's clever. And so if we run that, we have this in the right shape, hopefully. See, I only have 10 minutes left. So this is taking a little while. So while that's going, hopefully there are no errors. Let's continue with this code. So now the input shape is not going to be 784 comma, it's going to be 28, 28, 1. Great. One more thing, parameter that is worth including in this layer is when you do just simple convolutions, what happens is the output of your convolution step, its dimensions will be slightly smaller than the input. And so then as you have more and more layers, you will have, as your input is getting processed, it gets smaller and smaller and smaller. And that's just the way convolutions work. You can satisfy yourself that that's in fact the case by just going through it by hand. But one way to kind of get around that is to specify, to just draw a frame of 0 values around your image. And this kind of keeps the dimensions of the image the same. So 28 by 28, when you pass it through a convolution layer, the output is also 28 by 28. So you can do that by specifying that padding equals same. And since this is deep learning, we always have to have some nonlinearity. So we put in a nonlinear activation function. We could put the sigmoid function, but it is known to be problematic. So we'll use the ReLU function. All right, so that's that. And then we can put in a max pooling layer here. And then we can put in another convolutional layer. And this time, what I'm going to do is actually just copy paste these two. And why am I putting 2 layers instead of 1 or 3 or 10? That's another hyperparameter to think about. So in this case, what people tend to do is for the first layer, since you are learning relatively simple features, the number of filters you use is relatively small. But since you are then composing these simple features to learn more complex features, you increase the number of filters to be able to handle this increased complexity. So the only thing I'm going to do here is double the number of filters for this reason. And again, I do max pooling. And then what I want to do is, so the output of all of this so far will still be 2-dimensional. But what I want is a final layer of 10 neurons that's 1-dimensional. So to convert this 2D to 3D, sorry, 2D to 1D, I can just flatten this. And to do that, actually, sorry, I put max pooling 2D open close parentheses. That is wrong. You just do it max pooling 2D. You can import a flattened layer. And then so we put flatten here. So now we have a flattened object. And you can imagine that at this point, after all of this, when you flatten, the length of this vector will be really long. So I can go directly from this to my final layer of 10 neurons, but it's, people tend to, but that's quite an abrupt jump from something very long to something relatively short. So I can put in an intermediate layer, a linear layer that has an intermediate value. So again, I use a dense layer and I do dense 256, put in an activation. One side point I didn't mention was we put in an, actually we don't, this is a, I'm sorry, this is the danger with copy pasting. The input shape for the second convolutional layer should be removed. I wanted to say that this input shape, which is an optional argument, is only needed for the first layer. As long as you are putting in layers that are compatible with each other, Keras will work out what the input shapes for subsequent layers are automatically. All right, so we do dense 256 activation value, and then we have our final dense layer, just like our linear model, dense 10 activation. And remember, in this case, we want softmax because we want to have probabilities be the output. So that's our CNN model. And then we do the same thing. We do CNN.compile. We compile it. Loss equals, again, sparse, categorical, cross. Optimizer is Adam. Metrics is, again, accuracy. And finally, we can override our previous history object, or you can give it a new name if you want. I'm not going to do that. CNN.fit, and then we do X-train, Y-train. Give it a number of epochs. In this case, I'm going to do 20. And then validation split equals 0.1. Now, before I run this code, so I put 20 epochs and I I've mentioned now a few times the danger of overfitting. So one way to deal with overfitting is to use this early stopping callback. So we go up here, we can import from tensorflow.keras.callbacks early capital E and stopping capital S. And this is really simple. We use this early stopping to create an object that we just call ES. And what early stopping does is it monitors by default the validation loss. And the minute it detects that the validation loss is not improving, it's going to stop training. So this is a very simple way of avoiding overfitting. Because if overfitting is a function of too much training, early stopping is a sensible way to avoid overfitting. Now, early stopping can be quite exacting. Like as soon as it sees that there's no improvement in validation loss, it'll just stop training. And you run into the opposite danger of undertraining. So you can specify this parameter called patience that just says, give it, and you have to give it some numbers. In this case, I said 3. So what that means is, if you see the validation loss not improve or get worse for 3 epochs, like don't worry, like ignore it. If you see if it crosses that, if it continues to not improve or get worse, then stop training. So this deals with the sort of like stochastic nature of learning. Anyway, so ES is equal to early stopping patience equals 3. And then you can put this callback in your fit call. So you do callbacks is equal to, and then because you can put in multiple callbacks, again, you have to provide it as a list. So we do the open close square brackets and then ES. Then hopefully early. Invalid syntax. All right, given that we only have 3 minutes, I'm going to ask you to delete that because I'm going to have to look up why that is wrong. Remove the callbacks from here. And then let's just train for, let's do something simple. Let's just do 7 epochs, just because we're running out of time. And while this is training, we're just going to go ahead and this is going to be our submission. We can quickly evaluate our model on our test set. So to do that, it's simple. You just do cnn.evaluate. See that there's a question. Oh, thank you. Adam pointed, one of you pointed out that I forgot to put import on the early stopping import line. Sorry, I'm rushing. Thank you. Close. Okay. So this gave us 99.3. That seems pretty good. Ideally, we should look at the accuracy and loss curves, but I'm really running out of time, so I'll just assume that this looks good. So you do cnn.evaluate, and then we can do x_test, comma, y_test, and hopefully this should also work nicely. And it gives us, so I mentioned that this specific test set that people, that they provided is a, were made by different people. So don't be, this accuracy is actually pretty decent. They were saying expect, if you see around 76, 77%, you're doing pretty well. And we see 78.2%. So that's nice. All right, so time to submit in 2 minutes. So we have a submission file. And then we have our test set. So we have 2 things we have to import. One thing, so we'll import the submission file. We'll call it sample_submit. It's equal to pd.read CSV. And oops. And then because I foolishly call this thing test, X test, I'll call this, I don't know, I'll call this real test is equal to pd.read CSV. And that is test set. All right, so let's take a look at the sample submit. We see that there are just two columns here. So it has the ID, which we're supposed to leave as is, and then it has a label. And by default, it just gives the label as 5. That's just predicting that everything is a 5. That's kind of our baseline. And to see the real test, what that looks like, we do real test.head again. And we can see this is, again, very similar to our training set, except the first column is not called label, it's called ID. And the ID is just like 1, 2, 3, 4, 5. So again, what we can do is we can do real, again, we can just call real test is equal to real test dot iloc. And we need to pick all the rows and then just the pixel columns. And remember to convert it to NumPy. So I see that it's 5 o'clock. So if anyone has to leave, I'm sorry that I've run over. But what I'm going to show now is just how to make the predictions and then submit it for testing, for Kaggle to evaluate it. Real test. And what did we do? We divided it by 255. I appreciate that I can string all of this in one line, but sometimes it's nicer to just stretch it out. We convert it to float32 object. And then finally, we need to make sure, remember this is one dimensional, we need to change the dimension, real underscore test dot reshape x1, 28.28.1, and this should all hopefully give me no error. Okay. And now we make some predictions. And to do that, let me just show you what the predictions look. Oh, actually, we can just do predictions is equal to cnn.predict. And then we just do real test. We can take a look at the first few predictions. The first, I don't know, 3. We see that instead of giving us just one value per test sample, it's giving us 10 values, and these are the 10 probabilities. So what we can do is we can pick the winner, and to do that, we do predictions dot. We can use the Arg Max method. And Arg Max just means pick the index of the maximum value. But we need to specify the maximum value across what? Across all the rows or across all the columns? And the answer is across all the columns. So to specify that, we do axis equals 1. If we wanted across all the rows, we would do axis equals 0. And then if we look at predictions, the first 3 examples, say, would look like this. See, so the first 3 predictions is making a 302. Great, we are almost there. So we go to our sample submit and override its label column, which is just a bunch of 5s with our predictions. And then let me just quickly make sure that that worked. Great. And then finally, we can save this sample underscore submit as a CSV file. And we have to, the guidelines say we have to call it, I wrote it down, we have to call it submission, not submission, submission.csv. And remember to set the index parameter to false, because by default, if you don't set it to false, it will, let me just save this. It will save it as, the first column will just be like this ID, 0123. We don't want that. Okay, it's saving. I don't think we have to wait for that. Now, if you want to submit this, you click on save version. Version 1, I think this is all fine. And this is where if you have to leave, please leave. This is going to unfortunately take around 4 or 5 minutes. But I can describe what happens next. So what it's going to do is it's going to run through your entire notebook, which is why it takes a while. And it is going to make sure that there are no errors. And then you are ready to submit. And then once you're ready to submit, so you go like this and you have to click on show versions. and then you click on that page, you'll see a button for clicking submit. Click submit. And then finally, you'll have to wait another 2 or 3 minutes while Kaggle evaluates the performance of your model, and it'll give you 2 scores. One score will be on this data set, which is called public, but apparently for this specific competition, it also has a private data set. Yeah, and then you can, if you are happy with that, you can submit it. And your name and the performance will be posted to their leaderboard. You can see how you do. So while this is going on, thank you everyone for paying attention. I hope you learned something from this. This is a nice exercise and this is fine, but really the two, I find many benefits of Kaggle. Two immediate ones are, one, this access to GPUs, which is pretty great. And there are also these things called TPU for tensor processing units. I don't have much or any experience with them, but they have been specifically designed by Google. And I believe Kaggle is owned by Google anyway, to run these complex deep learning models. That's one big benefit of Kaggle. And the second benefit is just so resource rich, tons of data sets, competitions, as you saw, live competitions with healthy prize monies. And they have courses and things like that. Wow, that's actually done. I'm surprised. So that was just 2 minutes. So you click on show version and it gives you this nice kind of printout of your version. I believe you have to go to viewer. Yep. And then I think it's this ... submit to competition. So it's kind of hidden away, but that's what you click. And I'm happy with all of this. This is the name. You can change stuff here if you want, but I'm just going to leave it as is. You submit to competition and then view my submissions. And see, unfortunately, it's running the notebook. So you'll see the private score and public score appear in again in a couple of minutes. So I'm going to wait for that to happen, just because I'm curious to see what score we've got. And then if there are no questions, I'll call it a VLE. So while this is running, I'm just going to go back to our code here. So this CNN model, yikes. I mentioned early stopping, and thank you for pointing out that I didn't type import. That's one way of dealing with overfitting. We only had 7 epochs, but maybe if we trained it for 9 epochs, we'd do better, or 10 epochs. But that's kind of like, if you don't have guardrails to prevent overfitting, then you will very likely run into overfitting. So early stopping helps there. Then there are all kinds of regularization techniques you can use. Dropout is a common one. Batch normalization is another one. You can do L1, L2 normalization. Many options. But the point is, for all of those things, like if you, for example, wanted to put in dropout layers, and so what dropout means is you just randomly drop out neurons in your layers during training. And this, the effect of this is it makes your existing neurons, it makes them more robust. It builds in redundancy into the system. And to put in a dropout layer, you just literally import dropout and then just put it in after the layer of interest. You just type dropout. And oh, you have to give it a probability, like the number, the percentage of neurons you want to drop out or switch off. All right, this is still running. Maybe if I refresh my page, I'll see it. No, I think it's still running. The TensorFlow and Kara's websites are especially good for tutorials, and it's exhaustive, and they cover all kinds of complex things. Another thing that's one. Another thing I wanted to mention was learning from other people. So if you go to code, leaderboard. Yeah, you can see there's a private and public leaderboard. So someone got 99.6, which is incredible. But that's after 58 entries. So you can clearly tell the people, it takes a lot of time to get such a good model. Unfortunately, I don't think you can see that person's notebook, but some people make their notebooks public. So this person did really well, number 9. And so if you click on that, you'll start to see what they did. And one thing that we didn't do, we didn't do multiple things, but one thing that is commonly seen in these image classification tasks, or actually just sort of deep learning in general, is data augmentation, image augmentation. And you can do that really easily again in Keras. We just didn't have the time to cover that. All right, so we have a score of 97.97, a public score of 0.97, round up again. And what happens if I just, okay, we'll leave that at that. And just to get a sense of, see the leaderboard. Sorry, let me just go back to, sorry. Let's see, 0.97. I just want to see where that is. So that's, I think that's a really nice score, but unfortunately, because this is Kaggle and all of these people, there are some many professional programmers here and the very competitive people. You can see that, unfortunately, that doesn't put us in a very good position, despite the fact that we had such a nice, such a high accuracy. Anyway, we're kind of in the middle somewhere, but I guess that's it. So I'm going to give maybe like 1 more minute, and if anyone has any questions. You're welcome. All right, and while we're still in the final minute, let's just, actually, I'm curious to see the person who came in 9th, if it's kind of obvious what they did that was different. They put in, see, batch normalization. So I mentioned, so we use the sequential model. There's a functional API, and this is what the functional API looks like. It's called functional because you use the output of your previous layer as input for your new layer, just sort of like chaining functions together. And they used 3 layers. They used many more kernels than we did. They did some fancier stuff. Yeah, this is, wow, this is a, I wouldn't definitely not have had time to type out all of this stuff. And that's how they got 99. All right, thank you for your attention. And if you have any follow-up questions or things like that, please email me. I am going to make this notebook publicly available, and I can send the link via Tiffany if you're interested, but you're probably better off looking at one of these notebooks. But yeah, otherwise, thanks for your attention.